guess I can welcome everybody as they're coming on. Hello, everybody that's joining. We will get started as close to 7 as we can. But I think we're still watching the participant numbers jump up. So we'll get started shortly. Hello, everyone. Thanks for joining. Samantha, are you letting people in manually or do people just jump on? Cool. So we'll get started shortly for everyone just joining. We'll wait for a couple more people to jump on. Get yourself comfortable. I feel like we should have intro music. Everybody could just.
I agree. We'll add that to our list for next time. Get a solid playlist going.
All right, Becky, can you hear me? Hi, Becky.
Excellent. So we'll let people continue to roll in, but we do have lots to get through. So we're going to get started. So today we're talking about heat pumps for space heating, so home heating and home cooling. So we'll jump right into the slides. Today, we'll start it kind of as a webinar. So if you want to remain muted, you can keep your camera off, but feel free to type in the chat if you have questions. We're recording the meeting and we won't record the breakout rooms when we get there. So today's meeting, next slide, please, Lisa. So today's webinar was brought to you by the Residential Sector Committee. So we've got some names up here. I am Rebecca McIntosh. I'm a realtor with Coldwell Banker and part of the Residential Sector Committee. So a group of us have worked together to bring this to you. Heather McDermott is a climate consultant. Jeff is our guest speaker today, Monica and Lisa with Reep. So you'll see these names in the chat if you have questions, and we have an active chat. Any of these people, and even our breakout room facilitators, Jim, Anthony, Mary Jane Patterson, Sydney, and Colin you might see us all active in the chat this evening. Next slide. And then I'll turn it over to Samantha to explain Climate Action WR's role in all of this and give a little intro.
Thanks, Rebecca. So, hi, everyone. Thanks so much for coming out tonight. I'm Samantha Tremmel. I'm the Plan Manager with Climate Action Waterloo Region. And what Climate Action Waterloo Region is we are a local collaborative made up of community members, local organizations, and the municipalities that are within Waterloo Region. And our focus is on climate change mitigation, so reducing greenhouse gas emissions at their source. We are co-led by both Reep Green Solutions and Sustainable Waterloo Region. And we are funded by the region of Waterloo, as well as the cities of Cambridge, Kitchener, and Waterloo. But we also work with the townships as well. So a large collaborative of all of the municipalities and different stakeholder groups throughout the community. Our role is to coordinate the activities related to our community level climate action plans and strategies, measure progress, and engage the wider community in that work through events and projects and initiatives such as this one here today. So we are really fortunate to have a tremendous team of volunteers through our sector committees. These are volunteers who take on different projects and initiatives related to the 3 highest emitting sectors in our community's greenhouse gas inventory. So that's transportation, workplaces, and residential. And as Rebecca mentioned already, this webinar has been curated and presented by our residential sector committee. So we thank them for all their time and dedication that put into this work and for putting on this great event for everyone here today. And I'll also use this as a little plug to mention that we are currently recruiting for our 2022 sector committees. So if you are interested, you can find some details on the climateactionwr.ca website if you're interested in volunteering with us. Next slide, please. So our intention with this webinar here today is to share sustainability best practices to protect and promote stewardship of the land by sharing an introduction to what heat pumps are, how they work, and share lived experiences with the technology. I myself am a settler on this land, and through the Dish with One Spoon Treaty, settlers and Indigenous people alike have a responsibility to safeguard the land and water that we live on. And our intention with tonight's webinar is to share knowledge of sustainability best practices, largely from a settler perspective, to help others learn to be environmental stewards and fulfill our treaty responsibilities. And we hope to continue to learn how to integrate Indigenous knowledge and other knowledge systems into our sustainability education and actions. So land and territorial acknowledgement is only one small part of supporting Indigenous communities. And we hope that our territorial acknowledgement statement will inspire others to stand with us in solidarity with Indigenous peoples. We acknowledge that Waterloo Region is located on the traditional territory of Indigenous peoples, including the Haudenosaunee, Anishinaabe, and Neutral peoples. We recognize the enduring presence of the Indigenous people that we share this land with today and their contributions to our community. We value their traditional knowledge and how to live sustainably on this land we share and will leave for future generations. Climate Action Waterloo Region is committed to the necessary learning, relationship building, and actions to work towards reconciliation. And if you'd like to learn more about land and territorial acknowledgements, we encourage you to check out the Ellisburg Know the Land website. Next slide, please. So a little bit of background for tonight's webinar. So just this past June, all 8 municipalities within Waterloo Region endorsed Transform WR, which is Waterloo Region's transition to an equitable, prosperous, resilient, low carbon community. This is our community's long-term strategy to achieve an 80% greenhouse gas reduction by 2050. Next slide. So human-generated emissions can come from many different sources. However, most of our emissions here in Waterloo Region come from our energy use. We burn fossil fuels to power cars and equipment, to heat and cool our homes, and to heat our water. Locally within the region, 94% of our 2015 emissions were produced by energy consumption and combustion in 3 sectors: transportation, workplaces, and homes. And within these sectors, there's 6 primary energy sources that contribute to greenhouse gas emissions, with natural gas being the second highest at 36% of that pie. So as a result, addressing our local emissions is primarily about changing our energy use and the systems that supply that energy. Next. So in relation to how we heat and cool our buildings, the Transform WR strategy outlines 2 key goals. So by 2030, 20% of all buildings in Waterloo region will need to use electric heat pumps for heating, cooling, and water heating instead of natural gas, and 85% usage by 2050. So some ambitious but achievable goals here. And with that, I will turn it back over to Rebecca to segue into today's topic.
Thanks, Samantha. So now I'll introduce our guest speaker. So Jeff Hunter is going to take us through a presentation. He sits on the Climate Action Sector Committee and was part of bringing this together. He's also the Vice President at the Ontario Geothermal Association and founder of Evolve Thermal Energy. Jeff is a trained mechanical engineering technologist, and since 2005, he's been representing HVAC manufacturers in both the residential and commercial marketplaces. He provides education and training on design, installation, and service of ground and air source heat pumps. Jeff also teaches at Conestoga College on renewable energy and energy management programs. So today I welcome Jeff to take us through a presentation.
Thank you very much, Rebecca. Can everybody hear me okay? I'm going to check.
Yeah, good.
Okay, so I'm going to share my screen now. Stop 3, share. All right. So yeah, welcome everybody. Thanks very much. Just one thing before I start, am I stopping at 8:15 or 8 o'clock on the dot? I apologize.
We're going to do some breakout rooms. So we are looking for time to do breakout rooms before that.
8 o'clock. Okay. All right. So we have a lot to cover this evening. Thank you very much. We're talking about space heating technology, and it is a very in-depth topic. And especially with heat pumps, there's a lot going on. So here's my little agenda for today. And you can see on my agenda, I've got a couple of photos there. And these certainly aren't pieces of equipment that you would find in a typical home. But for those of us that are new to heat pumps, I wanted to just illustrate that certainly heat pumps aren't a new HVAC technology. Large commercial buildings, homes have been using heat pumps for quite a long time. And 2 projects here I've been involved with in the last little bit. The first one there is in the behind here is a school in London that actually just recently decarbonized their entire heating system by using these are ground source heat pumps here that heat the building, a large high school in the London area. And this is a chiller for a Fanshawe College building. It's 1,200 tons, a very large chiller, one of 3 that they'll be installing the next little bit. So these pieces of equipment operate on the same principles as the heat pumps we'll find in our homes. So I thought it was neat to just show you that. So, but first we're gonna go back and we're gonna talk about space heating technology, a little bit of a history, and then we'll get into why we're talking about heat pumps today. And we'll break it out into 2 separate sections. We're gonna look at air source heat pumps, ground source heat pumps, and then talk a little bit about Jerry Maguire, show me the money, and costs, operating costs, savings, all that kind of stuff. So let's get right into it. So how did we start with space heating? And I'm going pretty far back here to the earliest times of heating. And, the simplest ways, it's wood-fired heating. So going all the way back, this is where we started. Fire was the earliest form of comfort heating. Of course, it's still used today. And, if you look at Canadian homes, there's a smaller percentage of Canadian homes that rely primarily on wood heating. But when you have a fuel like wood, a source of ignition and oxygen, you can get combustion. And out of combustion, and depending on the fuel, you'll get a variety of products of that combustion or byproducts of combustion. And one of those byproducts is actually heat. And that heat is what we use to comfort heat us, or space conditioning. Now, that's very simplistic and way back. Let's fast forward 40,000 years and we have mastered fire. And this is fire on demand. Now, we're all probably familiar with this. Remote controlled fire, but think about how far we've come in 40,000 years. Now we can control fire with the push of a button. And there's really not that much that's different between this fire and the one that we looked at from 40,000 years ago. This one is essentially combustion. We're combusting a fuel, in this case, propane or natural gas. And byproducts of that combustion are vented out this fireplace outdoors. And another byproduct, heat, is radiated into the space for comfort or enjoyment. So how does that apply into space heating systems? Let's fast back to 1919 with the patent or the invention of the central forced air gas furnace. Now, there are a lot of similarities here between that fireplace that we just looked at and this gas furnace. This is basically a shell of the modern day furnace as we know it today. Alice Parker patented the central gas heating furnace in the US. This is a pretty basic form of a central gas fired furnace, but it burned natural gas that could be piped into the unit from a central gas grid. So that was an important deal. You could access a central energy grid and burn that fuel. It vented those harmful products of combustion outdoors, and the heat was delivered. So there's a heat exchanger inside of these furnaces, and the heat is delivered by convection. So hot air rises to the different spaces in the home. And it was actually pretty high tech because this original version had its own zoning system. So it was ducted to the different spaces. So it would be zoned out to different spaces in the home. If we fast forward to today, really not that much has changed with a central gas-fired furnace. I mean, it looks a little bit different. We've got ductwork here. We have our connection to the central gas grid. We have our venting. We're venting out the products of combustion. The technology maybe is adapted a little bit. We now have a blower inside. So there's a fan wheel inside here that forces the air, the heated air through the house. There's some fancy solid state, modern day controls in here that protect, safety controls and protect the home, because we are essentially bringing fire. We're bringing an explosion into our house contained within this box. So not all that much has changed, but I'll give credit to gas-fired appliances where credit is due. And I'm showing this image because I think this, from a residential gas-fired appliance perspective, a tankless water heater is the pinnacle of gas-fired technology. If you look at this box here, this heats water on demand. It'll take 5 gallons a minute of water. So think about that. That's, probably 2 showers and maybe 2 sinks running simultaneously. It'll heat that water from 50 degrees Fahrenheit, which is, groundwater temperature, up to 120 degrees instantaneously. And so that's pretty powerful stuff. The heat exchanger, the burner that these tankless water heaters use, is actually a ceramic material. So this will heat up to, about 2000 degrees Celsius when it's burning a flame here. And instantaneously after it extinguishes that flame, you could literally touch that burner with your finger. So it's crazy the materials that they put into this. And of course, the materials that go into the heat exchangers that make up how it heats the water. And, today with all technology today, you can talk to your water heater on your iPhone, and literally you can. This particular water heater is hooked up to Alexa. You could call Alexa and ask her to turn up the temperature of your hot water. So it's amazing what we have done with gas-fired technology today. And this product really illustrates that. The funny thing is that an average heat pump today has 2 to 3 times the efficiency of this equipment. Gas-fired equipment peaks out around 98, 99%. Because it's a combustion appliance, we can never get 100% efficiency because we have losses in that combustion process. And some of our losses are in the form of heat. We have carbon dioxide losses. We have nitrous oxide, sulfur oxide. These are byproducts of combustion that are losses from that process that get vented out to the outdoor atmosphere. They also prevent this system from ever being 100% efficient. The next funny thing about this is, when we're talking about heat pumps, a ground source heat pump from 1982 has more than 3 times the efficiency of this tankless water heater that was just brought to market in the last few years. So very interesting. I'll leave it there. Let's move forward. And with that, let's look at gas-fired systems. Natural gas systems in Canada in 2019 made up about 46% of heating systems. Heat pumps, on the other hand, account for about 5%. That was 2019. That's probably, this is all heat pumps all the way across Canada. It's probably in the 6% plus range now since 2019, because there are certain regions that are getting really aggressive with the adoption of heat pump. So what is a disruptive technology? And I want to talk about that with reference to heat pumps. A disruptive technology is a technology that affects the normal operation of a market or an industry. It displaces a well-established product or technology, creating a new industry or a new market. And I want to show here a reference to disruptive technologies, and I'm sure some people on the call have seen reference before because it's kind of common in this realm, but it explains a disruptive technology so well. This picture here is Easter morning, 1900. They have Easter parade in Manhattan, and circled in red there, if you can see it, it's hard to see, is an automobile. And all of the other people on the street and all of the horse buggy makes up everything else on the street. In 1900, there is one automobile. Now, this reference here to disruptive technology was actually first presented in a quarterly report from Tesla electric cars, to show the transition of automobiles. So the next picture is 1913, the same street. Can you see where the horse and buggy is? There's one horse and buggy on the street. So it took 13 years to go from all horse and buggy to all automobiles. So think about why that transition not only happened, but why did it happen so fast? The cost of maintaining and managing horses, upkeep, food, infrastructure, barns, labor, all of that convenience compared with the automobile, which eliminates a lot of those troubles and a lot of those hassles. Now we just have to buy a car, we hop in, and now we go. And we go farther than we ever have, trouble-free, relatively. So the value proposition to the consumer there really made sense. And there's of course countless examples of those types of transitions throughout history. And we're in one of those transitions right now. And heat pumps fall into that place. This is a chart of the law. It's called the law of diffusion of innovation. Any product or new technology that comes into a market generally follows this curve of diffusion of innovation, how customers or marketplaces will accept a new product. Now, we talked about 5-6% adoption of heat pumps in Canada. So that puts us into this neighborhood here. What's interesting about this is that we are now getting to the point of the curve where things really start to accelerate. And if you haven't been too familiar with heat pumps yet, pretty soon you're probably going to have a lot more exposure to them. And in fact, that's probably why you're on this call tonight, because you're starting to see more about heat pumps. So it's not an unusual thing. We are on the cusp of the fastest, deepest, most profound disruption of the energy sector in over a century. That's an organization, a think tank called RethinkX, and they're headed up by a very well-respected gentleman, a lecturer at Stanford, Tony Seba, and he's been accurately predicting technology disruptions and transitions since the early 2000s. He's been right. And they're talking about the overall energy sector here with respect to generation and how we use energy throughout the world. Homes and buildings are a major component of that. So we're well within that transition. And so what does that mean? Well, if we look back to 40,000 years ago, it's probably finally the end of the age of fire. And so that's what we're here to talk about. So why heat pumps then? Well, this is, we talked about a little bit at the beginning of the presentation about climate action WR, and I'm going to look at that a little bit here, but this is Canada as a whole, our emissions by sector. You can see oil and gas makes up a large chunk of Canada's emissions, followed by transportation, and then there's buildings. And that's what we're falling in here. Buildings represents, all emissions related to space heating, cooling, domestic water heating, and of course, other associated emissions with respect to construction and all of that. So it's interesting to see the total makeup of the Canada's overall emissions. If we look at a local level, homes and workplaces and other buildings make up about 45% of the region's emissions. If we focus in on a particular Canadian home and look at how we use energy in home, this is the typical pie. So most of the energy that we're consuming in the home goes towards space heating because we're a Nordic climate. Second most is water heating and cooling. Now, this is an average home, and we have to remember most homes out there are average. We're starting to see a lot more in the new construction sector for net zero homes, passive house homes, a lot more tighter homes. But when we're talking about existing homes, a lot of homes fall into this realm. And of that energy, most of that energy used for space heating is natural gas. And again, on the water heating side, most of that energy use is natural gas. And we can see some other fuels that are used, but predominantly throughout the country, natural gas is providing most of that energy. If we look at Ontario in specific, in 2019, about 66 or 67% of heating systems throughout the province, residential, use natural gas. This slide we saw earlier in the presentation, and this is the Waterloo region's emissions. So that natural gas is number 2, only to gasoline. And so I would suggest that buildings, space conditioning, heating makes up a large chunk of the GHG emissions that are captured here under natural gas. So where am I going with this? Oh, and before I move from that, I mean, natural gas, it's important to note, natural gas is primarily methane. That's the main component in natural gas. And as a greenhouse gas emission, methane is about 82 times more powerful than CO2 in the first 20 years of its life in the atmosphere. And so I'm not even talking about burning natural gas. I'm talking a lot about just getting natural gas to the building or wherever you're taking it to. There's hundreds of thousands of kilometers of pipeline that natural gas is transported to before it gets to your gas furnace in your home. And those pipelines, as we are now seeing a lot more in the media, are probably leaking more than we originally thought. And so when that methane escapes, it has a very powerful punch in the first 20 years of its life. Over 100 years, its global warming potential is about 28 times greater than CO2. So it diminishes after 20 years, but it's still much greater than CO2. So it packs a real punch up front, which is very damaging in the short term as we continue to emit. But it also means that we have a real opportunity to make a relatively quick impact on warming if we focus on methane reduction. That's why reducing our reliance on natural gas is so important. Heat pumps emit zero emissions at point of use. We're no combustion in a heat pump. We're just moving heat. The emissions associated with the heat pumps are contained within the manufacturing of the product, the materials that go into the product itself, along with any emissions associated with the generation of the electricity. So when tied to a clean electricity source, you can quickly see how incredibly effective heat pumps can be at reducing greenhouse gas emissions. And with that said, what does it look like in Ontario, our electricity generation? Well, thankfully, we've done a lot of work to our electricity generation in Ontario over the last 2 decades. This is 2018, the makeup of our electricity generation, most of it being nuclear, hydro, wind, our gas peaker plants in there at 3%, solar and other renewables in there as well. one interesting note. So we phased out coal-fired power generation. I think in 2014 was the last year that we had that. In 2005, and it's sometimes people don't remember, I'm thinking back to it myself. Back in 2005, the city of Toronto had 48 smog and air health alert days. Now there are none. Coal used to represent 25% of Ontario's electricity supply mix. And coal was a major source of air pollutants. So it's amazing what's changed on that scale. On the national scale, in 2018, 82% of electricity generation in Canada did come from non-GHG emitting sources. So we have a relatively clean electricity grid. Let's use it. So first, we're going to talk about air source heat pumps. Now, this photo I'm showing here is of an installation, Dorothy McCabe from here in the Waterloo area. Installation was done by Waterloo Energy Products, which we have Jim Bolger on the call this evening as well, and he'll be in the technical experts breakout room as well. But air source heat pumps are classed based on their configurations or how they're serving the house. And the one we're looking at right now is what you would call a central ducted air source heat pump. You can see heat pumps have, air source heat pumps have an outdoor portion and an indoor portion. And in the case of a centrally ducted air source heat pump, it comes into an air handler. I would call this an air handler that connects into the ductwork in the home, and contained within this air handler is a refrigerant coil as well as an electric backup coil. In the outdoor unit, this is exchanging energy with the outdoor air, either in heating or cooling. And within this coil, if we looked around back of it, you would see, within this unit, you would see another coil similar to the one that's in here, just structured a little bit differently. And that exchanges energy between the air and the refrigerant. So an air source heat pump like this uses the outdoor air as its source for heating energy in the winter and a sink for heating energy from the house in the summer. So essentially it's moving heat from the building inside in the summertime and rejecting that outdoors, which is essentially the same thing as an air conditioner does. Now, next type of air source heat pump that is an option is a ductless split or a ductless mini split air source heat pump. And these come in different sizes and different configurations. And again, similar to all of them, we have an outdoor unit here exchanging energy with the outdoor air. And then we have indoor mini split heads. Now, this type of application lends itself well to homes that don't have a central ductwork system. And there's quite a lot of homes in Ontario that are electrically heated, electric baseboard systems. So how do you move energy or heat around a building when you don't have ductwork? Well, mini split heads answer that question. And it doesn't have to be just one. In the case of multi-zone ductless mini split, and this is a particular manufacturer, but there are many manufacturers that offer these types of equipment where you have one outdoor unit and you match them up to a variety of indoor heads, depending on the application. Now, there is another type of air source heat pump, and it's probably best fit for systems that are currently on boilers using in-floor heating or cast iron radiators or baseboard radiators. It's called an air-to-water heat pump or an air-to-water cold climate heat pump. And the difference really is in where it exchanges its energy. So an air source heat pump, the ones that we just looked at, move heat energy from the outdoor air into an indoor airstream, whether that airstream is in a ductwork system or through the mini split head in the particular areas. This moves heat from the outdoor air into a water stream or a water source inside the building. And that water source would serve, this piping is in-floor piping that would be in your floors, and that water would be heated up and sent through that water circuit or a radiator circuit. We're going to talk about sizing and selection and all that coming up, but generically, there are heat pumps and air source heat pumps to service all types of applications. Now, to reference how a heat pump works, And if you're not familiar with heat pumps, if they're new to you, first of all, I'm going to say a gentleman by the name of Peter von Rittinger built the very first heat pump all the way back in 1856. And I would love to have asked that as a question to see where everyone knew the first heat pump was invented. I'd be curious as to what the answers we got, because heat pumps are still new to some people. But back in 1856, they used the heat pump to dry salt in salt marshes. So the technology obviously is extremely well developed, actually even more so than that central gas-fired furnace that was invented in 1919. So how do heat pumps work exactly? And it is a pretty technical thing. The refrigeration circuit of a heat pump, how it actually works is, you're not unfamiliar with it. You've seen it every day of your life for your entire life. It's very similar to how a refrigerator works. One second here. Sorry, I'm just pausing 1 second. My headset is, okay. So it's very similar to how a refrigerator works. First of all, what I'm going to do is define the components. In any heat pump system, you have a hot side and you have a cold side. And this is a very simplified image of what we're looking at. So it's a ductless split, mini split that we just looked at. Here's the outdoor unit. And here, it's hard to tell, but that's that indoor mini split head. So we have a hot side and a cold side. And what makes this a heat pump is the fact that we can switch hot side and cold side. So the outside unit can become the hot side and the inside unit can be the cold side, or vice versa. The inside unit can be the hot side delivering heat and the outside unit can be the cold side rejecting heat, absorbing heat. So it's pretty handy because we want to heat and cool our homes out of the same piece of equipment. At the heart of the system is the compressor, and it is a lot like a human heart because it is pumping up the pressure of the refrigerant inside the circuits of these coils. So much like you would see on the back of a refrigerator, and this is an old refrigerator, but it's the same tech as the new refrigerators. You have coils on the back of the fridge. Inside those coils is a refrigerant. So when we plug the heat pump in or we power it up with electrical energy, the compressor, the heart of the system, takes that electrical power and uses it to move either a piston or some type of device back and forth, basically squeezing the refrigerant inside a cavity continuously, many times a second. As it squeezes that refrigerant, the pressure in that cavity increases. And when the pressure increases, so does the temperature. There is a direct relationship between temperature and pressure. And so that refrigerant that leaves that compressor exits the compressor as a very hot gas. It's boiling hot, just like boiling water in a tea kettle and you have steam coming off the tea kettle that's incredibly hot. You'll burn yourself. That's the hot refrigerant gas. So that hot gas is sent to where, in this case, if you're heating, it's where you want to heat. So in this case, it's this indoor mini split head. And in the head of that mini split, it looks a little bit different, but is the coil that you have on the back of the refrigerator. So it's mashed into the head of the mini split. And then there's a fan in there that we blow air across. So as that super hot, superheated refrigerant makes its way into the indoor mini split head, the air removes the heat from the refrigerant and blows it into the living room, if that's where your mini split head is. So with the hot refrigerant gas in the coil, that heat is released into the airstream. As the heat releases from that refrigerant, so now the refrigerant's on its journey out of the indoor head, the refrigerant cools and it moves over now to the cold side of the system where we purposely drop the pressure of the system. There's a device in here that expands and drops the pressure in the system, and the refrigerant in the cold side of the system becomes really, really cold. Now it's primed to absorb heat. Even cold outdoor air is warmer than this refrigerant. It's super cold. So as it enters the outdoor unit, any heat in the air above the temperature of the refrigerant is absorbed. Now that refrigerant contains this low-grade heat from the outdoor air, even when the outdoor air is below 0 degrees Fahrenheit or around minus 23, 24, 25. This is what we're talking about with cold climate heat pumps, is they can absorb heat at those temperatures. So that low grade heat then comes back into that compressor, and that cycle starts again. That heart keeps beating, pumping up that pressure. Now, that process has to be efficient. We have to be getting more out of that system than we put into it. Otherwise, we would just use an electric heater, a toaster. We would plug a toaster into the wall, because when we plug a toaster in, we use 1 watt of energy from the grid or the electric plug, and we get 1 watt of heat that heats our toast or toasts our bread in the toaster. So if we're not more than 100% efficient with this setup, why do it? So of course, we are more than 100% efficient with this setup, with a heat pump. And for cold climate heat pumps and heat pumps in general, we're going to get into some graphs here, and I don't want to be too complex with it, but we define the efficiency of a heat pump through the term coefficient of performance. And basically, that's a calculation where we measure the output of energy in the form of heat versus the input of energy in the form of the electrical energy that we power, that powers the process. So the electrical energy we get from the grid, we divide that out, we get a COP, or coefficient of performance. And you can see along this chart on the Y scale going up here is our heating COP. On the X-axis, this is our outdoor temperature. And I apologize, it's not in metric. This is American chart. This is taken from a study done in New York State a few years ago in December 2016. So the temperature is along the X-axis. And we can see at minus 10 Fahrenheit, I guess that's about minus 23 or so Celsius, our performance on a cold climate heat pump, the blue line, a normal heat pump in the red line, is about 1.5 or so, minus 10. And a typical heat pump is a little bit less than that. Now, I would suggest that, 2016 was 5 or 6 years ago. There's probably a little bit of development in air source heat pumps since, but I wouldn't say it would be a dramatic change. Today's air source heat pumps would probably be from somewhere in the same range, 1.5 to 1.8 or so. Now, keeping in mind that an electric toaster is 1. So we can see that temperature has an impact on overall performance of a heat pump. All right, efficiency. And, we can also say 1 as a percentage, 100%. 2, 2.0 COP is 200%. 3, 300%. So keep that in mind. Now, I know there's a lot going on in this chart, but it's very important because air source heat pumps are also characterized by how their capacity changes with outdoor temperatures. As it gets colder outside, it gets more difficult to extract that energy from outdoor air. And as we saw, the air source heat pump also becomes less efficient, that coefficient of performance. Cold climate rated heat pumps, air source heat pumps, have allowed the equipment to operate at lower and lower outdoor temperatures down to that minus 25 or minus 30 point, but we still have to be cognizant of its capacity. Now, we've got a bunch of stuff happening on this chart. I'll try to point it out here. The blue line is our house. That's the heating requirement in our house. If you look at the bottom of the chart, to the right is warmer. This spot right here, we don't need any heating at all. It's probably 10 or 15 degrees Celsius, somewhere in there. The house is just sitting, no heating, no cooling. Over here, it's colder, way colder. In fact, up here, this is our heating load on the Y-axis. Up here, they call something design heating load. That's how we size heating systems for buildings, this design point. It is essentially almost the coldest day of the year. So how much heat do I need to put into my house on almost the coldest day of the year? That is our design point. So as it gets warmer out, the heating requirement for the house decreases. The red line is a heat pump output capacity. It is just a generic line. There are many heat pumps with many capacities, and if we plotted them all, we would see red lines all along this line. The point where the red line crosses the blue line is called the balance point. That is where the heat pump output capacity at that outdoor temperature completely satisfies the building load or the house load, the heating load. As it gets colder out, the air source heat pump doesn't have enough capacity to meet the heating load. So a backup heating system needs to kick on. Now, as I suggested, this capacity in this line we would have multiple capacities out here. The challenge for the designer of this system, the contractor, is to find a balance between the heating load for the heat pump in the house and the cooling load, because the heat pump's also going to do cooling. Our cooling load is always typically much smaller than our heating load. So we have to balance between the two. And of course, at some outdoor temperature, the heat pump will not be able to satisfy any more of the load, and it will fully shut off and switch over to a backup heating system. And not all heat pumps will have that. A lot of Aerosource heat pumps will continue operating way down load in conjunction with an electric heater, those cold climate heat pumps. But at some point, the backup heating system is doing the majority of the heating. And that's where you see the impact on that lower COP rating. Now, one more chart, just to give you a bit of perspective on percentage of loads or percentage of the year that heat pump will heat the house. And that's what this chart tells us. In Kitchener-Waterloo, this is different climate zones in Canada. Kitchener-Waterloo, we are cold, humid, so we're on this green line here. Now, if we had a heat pump that was sized to, an Aerosource heat pump sized to a 15-degree Fahrenheit balance point temperature, which is minus 10 degrees Celsius. So this temperature here, where the heat pump can no longer, well, if you go beyond it, the heat pump can no longer meet the load on its own. So if that minus 10 was that point, essentially the heat pump is handling 76% of the annual heating requirement of the home, right? So we can select at a lower temperature. There are trade-offs. There are economic trade-offs, because now you're going to have higher capacity equipment to get this balance point temperature lower and lower so that you handle more of the load. You're going to have larger equipment. You might need larger electrical, larger ductwork. So there's a lot of impacts there that the designer needs to put into consideration. Let's look at ground source heat pumps now. The fix to all that is a ground source heat pumps, because they operate off this stable temperature in the earth. So we don't have to play that balancing act so much with a ground source heat pump, because the outdoor air temperature isn't affecting the source side of the system. You can see our heat pump is contained in the basement of this house. It's connected to a piping loop that's buried in the ground, and I'm going to show you different configurations. But this particular piping loop is a horizontal loop, and we move a fluid through this piping loop that is, in the heating season, colder than the ground temperature. So the heat wants to move into the pipe, in the fluid in the pipe, and that comes back into the house, into the heat pump, where that refrigeration process, or that heat pump process, works to absorb that heat. And then, much like the Aerosource heat pump, it also reverses for cooling in the summer, taking the heat from the house and rejecting it to this ground loop as well. What does it look like? It looks a lot like a refrigerator. This is one example of them. The great thing about this is all contained within the basement. Ground source heat pumps typically use a central duct system. You'll typically connect these to central ductwork. Mini split heads is not really a thing for a typical packaged ground source heat pump, but there are ways to work around those applications. You get a little pump pack here. This is, it's kind of like a gas meter. It's a new age gas meter without burning the gas. All this does is move energy. That's all a gas meter does too, except you have to combust the gas to get the energy out of the gas. Here, we're just moving fluid around the ground loop and absorbing heat from the ground and moving it into the heat pump here. The heat pump absorbs it, boosts it up, and supplies that heat to your ductwork system over and over. Now, this is a water to air heat pump in a centrally ducted system. There is also water to water. So we looked at Aerosource air to water heat pump. Well, there is the same with a ground source heat pump, water to water. So that is an option as well if you have in-floor heating system, radiator system, snow melting, pool heating, whatever you want to do there. Backup heating is built into the inside of this system, but it's not used the same way as we described with Aerosource heat pumps. It is used mainly to benefit the first cost economics of the system, to keep that cost reasonable, And in the case of a problem with the system, it can act as a emergency heat. So it's not used to provide that auxiliary heating because we can't meet the heating load. Just examples of real life cases of horizontal loop installations. This, if you're calling in from an urban area in the cities, not for you. This is rural applications where you have some acreage to do this. I mean, these trenches are about 300 feet long. Got a bunch of pipes in here, so they take up a bunch of room. I mean, we can cut the length down and move them back on themselves and keep them in a more condensed area, but they're generally pretty destructive to the surface. There is directional drilling systems now, and they're a little bit higher cost than excavation to use, but they're lower than drilling, which I'm going to show you in a sec. You don't have to disrupt the surface. You can directionally drill beneath the surface and shoot the pipe under the ground. So if you have landscaping that you don't want to destroy, that may be an option. Now in the city, in urban areas, it very much is a possibility to install geothermal, a ground source heat pump with a vertical heat exchanger. This is a home that was fully deep retrofitted in the uptown Waterloo area. Now, this is an older home, so insulating the envelope was a necessity, improving the windows and doors, sealing up that envelope to get the building heating load as low as possible was basically a necessity. And you can see they just drilled this loop in the driveway. So it can pretty much go anywhere. In the region of Waterloo, there are particulars about installing closed loop heat exchangers, and there's areas where you can and can't do it because we sit on a large drinking water aquifer that has protection guidelines around it, so we have to adhere to that. But I mean, outside of that, anywhere you can punch a hole, you can get energy, and so that's a very powerful thing. Now, the equation of the COP, so a ground source heat pump efficiency is rated just like an air source heat pump off of a COP. And essentially, this is a very simplified look at it. Our heat pump is powered by electricity that we plug into the wall. So that's 1 unit of energy. We get about 3 units of energy from our ground loop. So that's the free thermal energy. So just by circulating the fluid around that pipe, that fluid absorbing the thermal, that low-grade thermal energy from the ground provides us about 70–75% of our energy for heating, cooling, and hot water. So 1 and 3 equals 4. So that's a 400% efficiency, 4.0 COP of a ground source heat pump. That does not change with outdoor temperature. And this is a great view of it here. This was done by Enertech Global, which I showed the picture of the air to water earlier. So they did this chart here, and it really shows the difference between air to air. That's their air to water, because using water as a heat transfer medium is much more efficient than air when you can use it. And then the geothermal system on top. So it does degrade somewhat, and they're showing that with outdoor air temperature. So there's a little bit of an impact at that ground depth, but not as much as an air to air. Now, I would suggest that today's best cold climate air source heat pumps probably fall somewhere in between these two, the blue and the gray line, because they have this capping out. There it is, that 1.0. There's that electric heater at, about -8. So I'd suggest that there is a better efficiency cold climate heat pump somewhere in there. Okay, Jerry Maguire, show me the money. We talked about this before we did this presentation, and we, it's a tough thing to talk about because every house, every application is so different. So how do you put a number to a generality? But this week, I don't know if you read the Globe and Mail this week, an article came out where somebody provided their costs. So I said, it probably makes sense. Let's use that. The gentleman had a house that was built in 1891, a 2.5-story house in Toronto. And so obviously the house needed significant improvements to the building envelope and the mechanical system, the electrical systems. Like, this was a massive project. And so I think it's important to note that in the Waterloo region, the majority of homes, if you look at the volume of homes, were built 1980, 1990 beyond. And so they have a reasonable level of baseline insulation. So the improvements that you would have to make are going to be much less than these folks made in their 1891 house. So they put the total cost around $43,000. Design, mechanical design, equipment installation, electrical plumbing work. So they had some significant work there. I'm really focusing here on the cost of the mechanical equipment installation. Includes, they did a central ducted air source heat pump. So 15.5, I'm looking at that. I'm looking at the duct work improvements. So they obviously had to do some significant duct improvements. I'm looking at the electric heater. I'm kind of totaling all those together. They've got an auxiliary heater, another mini split heat pump. So they probably had an extra room that they wanted to condition off of that. So, you know, it's significant, but if you break out what a typical home might be, I'm looking more to this number plus this number and maybe a little bit of this. But I mean, as part of their process, the energy audit, which I'm going to touch on at the end of the presentation, is incredibly important. I know we got 5 minutes here because it identifies areas where you need to tighten up and save energy. And if you do that ahead of time, that will only benefit the sizing and costs of the heat pump system. But if your house is relatively new, the improvements are probably a little bit less necessary or less impactful. So if you remember this one, we'll go back to this one. This was a more typical home. You know, it's a newer home. The duct system was probably more suitable. So the modifications they probably had to make, and Jim can probably talk about this in the breakout room, but they probably just did the supply plenum, a little bit of modification there, return air drop, that, you know, assuming the duct system was fairly existing. So this example was about, you know, $13,000 or $14,000 installed. So it's a much different cost. Ground source. Well, you know, what's the difference between ground source and air source from a cost standpoint? It's the infrastructure, right? And the unfortunate thing, you know, when you look at infrastructure in the gas industry, the gas company pays for all that infrastructure. They pipe it right up to the house. They give you the meter, and then you just, you know, pipe onto that meter and they feed you the gas. Well, with Geo, we kind of have to put our own infrastructure in at this point, and that has to be covered. So, you know, again, it is super hard to figure out all these applications and what the cost might be. I might put an average house in a rural application, you know, somewhere around $8,000 or $10,000 for a horizontal loop installation. Vertical is way more unpredictable because it's totally dependent on ground conditions, the makeup of the ground, what type of drilling we're doing there, not to mention how much drilling we have to do. So, you know, I might put that for an average house in the $15,000 range for the loop side of it. So you would have to add that on to the air source heat pump component, because the inside equipment is probably pretty similar between an air source heat pump and a ground source heat pump. So take the air source cost, you know, plus the infrastructure, that'll give you more of a glimpse of a total cost. Now, when we're looking at cost comparison factors into our economics, and we're at 7:57. So I'm watching the time. Oil and propane. So this is probably a fairly average house. I mean, oil, 90 cents a liter I had it at. This was in the summertime. I think it's probably higher than that right now. I had propane at 65 cents a liter. So we're looking at, you know, almost $2,500 for this average house. I don't know, it's probably, you know, 1,500 square foot, 1,800 square foot, reasonably well insulated. Propane in there at 65 cents a liter. Here's our air source heat pump. We'll come back to that. Our geothermal, this is interesting. Geothermal natural gas. Geothermal heat pump, ground source heat pump, is the most efficient heating system on the planet today. And a typical natural gas furnace that's available today typically is the same price operating. So something there is not quite right. And what it is natural gas is incredibly inexpensive at the moment. We are not paying the true price of natural gas by any stretch of the imagination. If we were, this would be much more expensive. And, you know, carbon pricing is going to adjust that because we're not paying to dump into the open sewer that we're calling our atmosphere right now. So that's going to adjust for that. The one thing I just want to comment on, so there is a bit of a delta between this air source heat pump and geothermal. I'd suggest that perhaps the top tier cold climate air source heat pump might shave a couple $100 off of this one. They might be a little bit closer in operating cost today. So that's something to note. Carbon pricing as of today, what are we are at $40 a ton, I think, in 2021. So that means we're about almost 8 cents per cubic meter on natural gas. That's the impact today. By 2030, it's going to increase. Carbon pricing will be $170 a ton. So the impact on natural gas will be 33 cents a cubic meter. So the average, I think I have that number wrong there. It should be 33 cents per cubic meter. So it's going to be significant for the average consumer, about $1,000 more annually for heating with natural gas for the average home in 2030. So if you're not looking at moving to an electrified system, there are going to be some major impacts for you. And that doesn't even account for any price increases for the supply of natural gas as a commodity. We've seen that, how dramatically those prices can change, and any gas supplier price increases, right? So there's a significant cost increase coming for natural gas. So we looked at the two operating costs. I know I'm right at 8 o'clock here. I might not get to my last slide. When I look at the differential in operating costs, it wasn't that large between a cold climate air source heat pump and a ground source heat pump. But if I'm a homeowner and long-term costs are my concern, and you want the most stable investment option, a ground loop, life expectancy is 70 plus years. That is energy that will always be there 24 hours a day, 7 days a week, on demand at the push of a button. You have, I don't know, about 70% of the thermal energy you need for your home for life. It's right there. That heat pump in the basement is expected to last 20 to 30 years. The air source heat pump, it sits outside, it's in the cold, it's in the rain. We'll give it 15 years and then you're replacing it. So what that means is you're buying 2 air source heat pumps in the period that you're going to apply 1 ground source heat pump. So you need to look at it a longer term cycle. And that always consistent high efficiency of that ground source heat pump insulates you from electricity price increases. So that creates that stable energy cost long term. Budgeting energy it will be a big thing as energy becomes a bigger piece of the pie, especially if you're staying on natural gas. Your monthly budget's going to change. Geothermal stabilizes that. For any utilities or municipalities or policymakers on there, geothermal increases utility baseload, so brings that baseload up, but shaves those nasty peaks that make power generation inefficient. It's a very win-win for geothermal utilities. And the truth of the matter is, on this whole perspective, if all we do is install air source heat pumps to electrify space conditioning, the cost of electrification will be way too high. Geothermal allows for a significant societal cost savings in that reduced grid upgrade or expansion requirements, because we're moving all that energy load from the gas grid to electricity. Geothermal allows that to be done way more efficiently. And that's been detailed in recent studies by Dunsky Energy Consulting and HRAI. Now, this is a last minute thing. I know we're at 8:02 and it's Jim Bolger from Waterloo Energy Products gave this to me last minute, and it is a very interesting proposal. It talks about net zero energy buildings and what is the best approach. I'm watching on my screen here because I can't read it on this one. So if we look at the first case, a hybrid scenario, this is my last slide, with a natural gas fully modulating furnace, 2-ton 19 SEER cold climate air source heat pump, and it's switchover temperature at 5 degrees Celsius. So it's going to look after all the air conditioning, and you also have a heat pump water heater. So the point is here, we want to get to net zero. The amount of energy we're using is the same as the amount of energy we're generating on site. So we're talking about solar PV integration as well to offset those watts. So our air source heat pump, cold climate air source heat pump for heating is using about 2,100 watts. We are using backup natural gas, but we have to account for that energy in our equation of net zero there. So we got to convert natural gas to equivalent kilowatt hours. And Jim has done that here. So that's 15,000 equivalent kilowatt hours. The carbon emissions, we also have carbon emissions on site because we're burning natural gas. So that's about 3.2 tons per year. So the total kilowatts for cooling, 706, and then our heat pump water heater, 1437. So that means our peak kilowatt demand in heating or cooling is 2.7 kilowatts. And that's like that low because the gas heating is providing our peak demand in heating. So the total annual equivalent kilowatts is 19,000 and change. So what size PV array would we need to offset that demand? Well, Jim worked it out to about 17 kilowatts at a cost of 2,800 per kilowatt. That's 47,000 bucks. So let's look at scenario number 2, cold climate heat pump. We got rid of the gas furnace basically, and we've sized a larger cold climate heat pump, still an Aerosource heat pump for domestic hot water. Our numbers go to about 8,400 kilowatt hours for heating, 700 for cooling, 1,400 for hot water. It's the same. But now our peak demand is 9.7 kilowatts. It's much larger. So total yearly kilowatt hours is 10,000, just over 10,000. What size PV array to offset? Well, 10 kilowatt at 2,800 per kilowatt. That's 28,000 bucks. Number 3, geothermal. Here's the real impact. A 4-ton geothermal system, same size as the cold climate system, with the domestic hot. Oops, I knew I was going to do that. With the Aerosource water heater. Now our kilowatts for the ground source heat pump, because it's so efficient, 5,100, 5,200, cooling 687, preheat hot water 525 for a peak kilowatt demand of 3.16. So our annual kilowatt hours usage 6,380. So what size PV array? Well, 6 kilowatts at 2,800 bucks. That's 2,800 per kilowatt. That's 16,000 bucks. Well, that just paid for your ground loop for those of you that want to go net zero. Okay, so we talked a little bit about the Greener Homes Grant, and it is out now, and it is providing funding for heat pump retrofits. So moving folks from natural gas into electrified systems. But a very important part and the start of the process is the energy audit process, assessing the envelope and the structure of the building to figure out where you're losing energy and where you can improve before you install a heat pump. It's always a great idea, and that's why they baked it into the start of the process here. So here's a snapshot of the rebates, and I will leave it there.